Thank you all for joining today. Yeah, just to clear the air on that, this is no more proprietary and confidential than anything else that will be posted to YouTube. So no, I did not realize that text was there on my template. But I'll be here to talk about some data corruption bugs that I fixed or in the process of fixing, and talk about how I diagnose things like this and perhaps the sort of tests that we could introduce to hopefully catch them earlier next time some of them were quite old. Bit about me, I'm Noah Misch. I'm a PostgreSQL committer. I've been working on PostgreSQL patches since about 2010. Before that, I was a DBA, app developer, that kind of role with Postgres. Took me about 5 years of using Postgres to encounter a bug. So when I encountered one and reported it and went through that process, it was so much fun. I just said I better keep having fun modifying Postgres. And there it was.
It's impossible to tell whether you're being sarcastic.
No, that's pretty accurate. That's pretty accurate. And Robert Haas is a big part of reviewing my first patches. So thank you, Robert. I'm not sure I would be there if you hadn't made that as pleasant as it was. So I'll mostly today be talking about things that one could discover and diagnose through the amcheck contrib module. This is a module that provides, among other things, a function called bt index check that validates a btree index. That's the main area today. Google customer reports led me to each of these initially, but then I needed these tools to really figure out what was going on. There are other sources of information about potential data corruption activity, so I'll just mention them briefly. If you have core dumps from your crashes, those can be quite informative. If you fail a recovery, then often the log messages from that failure indicate some kind of corruption. Also, just the general Postgres log, anytime it logs something with SQL state, data corrupted or index corrupted, pretty good indication that at least the author of that message thought it was an indicator of corruption. But each of those could be their own talk. I'll be mostly focusing on amcheck. Before we actually get into the individual fixes, I wanted to do a bit of a walkthrough of using amcheck and some tips and tricks to put some context on that. So this is to introduce the structure of a btree index. This will be familiar to many of you, but btree index has any number of levels. Each level is a population of 8 kilobyte pages that share a distance from the leaf level. There's one leaf level. That's where the index entries actually point to heap tuple identifiers. Then there are 0 or more non-leaf levels. In those, instead of pointing directly to the heap, they point to some page in the index one level closer to the leaf. That's the general structure there. amcheck works through this by performing a breadth-first search. The numbers up here represent the traversal order that amcheck will use. And as it does this, it checks a number of invariants that could be violated. So, for example, it will check if tuples are out of order by comparing the index columns within those tuples. So, index column usually the same as a heap column. If you have an expression index, it could be the result of that expression. Some sort of more obscure things to test, things like tuple identifiers out of order within a posting list. I'll get back to posting lists in the context of one of the fixes that I'll talk about later. So that's all tuple level things it detects. It also detects page level issues, connectivity problems within the pages, like a non-leaf page pointing to an index page that's not at the level it should be at. It finds pointers across pages to deleted blocks in the index that are not expected. And then there are some optional things. There's a new option in v17, check unique, which also does heap visibility checks to determine if a unique index has duplicates. And there's a much longer available one called the heap all indexed option. This overall goal is to detect a case where the index is missing a record for something that's in the heap. And the way it goes about doing that, kind of diagrammed at the bottom here, is that it populates a Bloom filter for every group of index columns that it observes in the index. And then at the end, it runs an index build heap scan, the same kind of scan you would do for a create index command. And every record that that scan generates, it then compares against the Bloom filter. And if the Bloom filter tells it this could not possibly have existed in the index, then that's reported as an error, as though the index is missing a record. I'm ignoring a few other features. There's a feature called root descend. There's a parent check feature, but we can't cover everything. So amcheck found all but one of the discoveries that I'll be talking about today. And in particular, heap all index, the option found almost all of them. So I recommend treating heap all indexed kind of like a default on. You can use the off version for some amcheck use cases. For example, if you're mainly interested in whether your storage subsystem is crash safe, probably heap all index off will detect it if it's not crash safe and you've crashed while you're modifying an index. But for more subtle things like whether you changed an expression in a way that violated its immutability, heap all index is the main thing that helps you detect that. I will note that if something's only detected by heap all indexed, it's probably a less severe form of corruption than the kinds that are detected without that option. Because if you have rows out of order within your index, just one row out of order can then conceal a large volume of other rows and make them unreachable. Whereas if you're just missing an entry for a row, that's generally going to have impact limited to that one row. A few other things to note. I like to enable debug one messages for amcheck because that highlights some unusual situations that are not corruption but can be informative. Another thing I always do is raise maintenance work mem to 1 GB before you use amcheck with heap all indexed. The reason for that is that the maintenance work mem drives the size of that Bloom filter, and for a table of significant size, it's easy to make your Bloom filter reach 100% bits set if you're using, say, maintenance work mem 64 megabytes, the default. So at that point, it cannot possibly report any errors because the Bloom filter thinks every possible value exists. So definitely set to 1 GB before you use that feature. So that's amcheck. Once I have an error from amcheck, that's usually not enough to figure out what's going on. I then usually turn to the pageinspect contrib module, which I'll talk about a bit later. Now here's an example. You can experiment with amcheck by creating some of your own corruption. I find it easiest to do this by creating an expression index and then changing the expression in a way that violates its immutability. So that's what I do in this example. This kind of corruption, you do need to use the heap all index option in order to detect it. Now, if you'd asked me about this before I got started, I would have said this would be one of the most common ways to end up with a corrupt index. I would have guessed like half of customer cases would be about this, but it actually has not been my experience. PostgreSQL bugs have so far dwarfed corruption from users changing their expressions in a non-immutable way. Can certainly vary a lot from one population to another, but that was a humbling experience. So I mentioned pageinspect. That's what I use next. So this continues the previous example. Let's say I find out that amcheck tells me heap all indexed has found that you're missing a record. Okay, what do I want? What can I find out about that? Well, there's really two big categories here. One is that there is actually some index entry that refers to the heap tuple ID, but it doesn't have the right key. And then the other case is there is literally no index entry referring to that heap tuple ID. And to distinguish these, I use the query here where we pull out the index in the form of a list of every group of columns as well as the tuple ID represented there. And then I can join that to the actual heap tuple IDs. And then we see here there's we have both the index's view of what the key actually is in the index as well as the heap's view of what the key should have been. And in this case, I corrupted the index by switching between a no-op expression and a bitwise complement expression. So we see that difference between the wanted index key and the gotten index key. So this is great information when it's available, because then I can sort of narrow down, okay, something created an index tuple at some point, but now it's the wrong index tuple. And if there's actually been none, then we would have had a null in here instead of a match. Now, excuse me. Pageinspect can do considerably more than this. There's a bt page stats function that's useful for like page level invariant violations, because it can extract page LSNs, it can extract the links to the btree siblings. I'll come back to that in the context of one of the fixes. Another thing I've done with pageinspect, you can kind of use it as an ad hoc sort of amcheck for other access methods. So on one occasion I had to corrupt gin index. We don't have amcheck for gin, but you could extract the heap tuple identifiers from the posting lists in gin and then map that back to the heap to try to understand how we got one missing. So I'll take a pause here. Does anyone have any questions so far? Okay. I will pivot towards some of the recently fixed or upcoming fixed corruption bugs. So this one was fairly straightforward, just to get started easily. pglogical, the extension, has some C code that updates a internally created table called sequence state. It does this without calling the function that updates indexes. So as soon as there was a non-hot update, the index appeared corrupt to amcheck. pglogical itself never actually index scans the table, so their fair chance has never harmed any users, but nonetheless, good to get that solidified. Here's one that's a little more interesting. PostgreSQL v13 and later have a btree index deduplication feature. That works to conserve storage by storing only one copy of a key when you have many rows sharing that key. And it's not done under all circumstances. It arises to when you do a page split to avoid that. Now, it's only a valid optimization for types where equality has the same semantics as memcomp. That is to say, equality, logical equality of the type is the same as bit equality of the type. Now, there's a data type called interval that opted in to deduplication. However, it did not follow that property. Yeah, because in an interval, you can have the value 24 hours and you can have the value 1 day. And these types are considered logically equal for hopefully obvious reasons, but they don't represent the same bit pattern. And the consequence of this is if deduplication had happened, an index-only scan might return a value like 24 hours when the correct value to return was 1 day. The query here just sort of illustrates the pageinspect output from a deduplicated index. This one involves an integer, so there's no actual corruption, but that gives you a sense of what you'd be looking at.
I don't actually understand that output.
So the data column is the integer value, so it's like the integers 1 through 8 as least significant a byte format there. And then the TIDs are the rows that, the heap tuple IDs that have that particular value. So integer value 8 appears in heap tuple 09 and heap tuple 018.
So we would want this list to have we would want the output to have an array of length 1 on every line?
So this output is actually fine, but for an interval data type, we should not be getting, yes, we should only be getting an array of length 1 for the interval data type because it's not properly deduplicable. But the integer data type is deduplicable, so it's totally fine that we have arrays of non-zero length. Good question, yeah. In terms of what this looked like diagnostically, amcheck would report that there was a heap tuple with no index tuple, but then running a pageinspect type query would find that, yes, indeed, the heap tuple does exist in some row. It's just doesn't have the right index columns associated with it. In terms of how we might detect this better, non-trivial tests do in fact fire an existing assertion if you mix values like 24 hours in one day. So I think we had pretty good testing concepts behind this. It's just that our test suite didn't happen to mix those two values in a way that actually reached them. We could put the assertion in a more frequently called function, like say have the btree comparison function could do a memcomp check on types that are supposed to be deduplicable. But I think overall, we just kind of got unlucky in terms of not reaching this one. But I will say in general, while we have pretty good coverage in terms of reaching each SQL callable function in our test suite, we don't necessarily have great coverage for testing all these corner case values that are unusual within a given data type.
I actually get later, but I had a question about testing. So, I mean, you're mostly doing index corruption examples, but one thing that I found is that it's pretty hard to test to look at various errors in, like, for example, corruption issues that would trigger an error in hot pruning code, that it's pretty hard to test them. And like we have tests, but adding new tests to that. So I wondered if that was sort of inherent in like testing data corruption scenarios is hard because you have to do the complex set of steps that would cause that to happen, or if you think there's a better way that it could be a different test suite or I don't know, whatever.
Yeah, to me, once you know how a given corruption thing happens, it's actually not too difficult to write the tests. The challenge is more like, how do we cast a wide net so that we actually catch the data corruption things we didn't think about? Right, exactly. And I do have some ideas later, but no, it's good. Yeah. So this one was a pretty different area. In recent versions, starting in I think V15, create database has a new mode of operation called strategy equal wall log. And that code has some special cases for non-relation files, which are currently pgfilenode.map and pgversion. And the special case for pgversion lacked an fsync for it. So the next OS crash after the next checkpoint could leave pgversion empty or missing, and the database would then refuse connections. Now, in theory, this is actually really easy to repair. You just copy pgversion file from any other database or just recreate it because it's a trivial ASCII file. But you need to kind of know that that's the only corruption. So yeah, I was not willing to recommend that until I understood what was going on. Preventing this kind of thing, testing for it, is fairly difficult. I did use the LazyFS piece of software to sort of confirm what was happening. But that mostly works well for this because only one thing ever writes the pgversion file at database creation time. So if you miss the first fsync, you'll never get another one. But it's a little harder to detect cases where, say, a file should have received 13 fsyncs and instead it only received 12 in a given test runtime. So LazyFS not as good for telling us about that. Incidentally, there was a bug recently where Run-End Dunkloud did some great work on a problem like this. That was a PGSQL bugs thread titled FSM corruption. I think probably fuzzing is the way to go to detect things like this. So but this one's pretty difficult. Sort of a fun bonus fact, I learned that we don't actually document device snapshots as a valid backup method, but it has been sort of circulated among the community and community members for a long time. So I expect they'll keep working. Maybe we should document them as something that we expect to keep working. That investigation then led me to another one, 2 other data loss vectors actually. In our README file for the transaction manager subsystem, we document several known code patterns for write-ahead log coding. And both of these corruption vectors involved patterns that were not documented there, but were in use. Shocking, right? So this table illustrates one of the vectors. Each column here is a different process running concurrently. And each row you can think of like a timestamp. Everything in one row happens before anything in the next row. So the trouble happened when a checkpoint and a backup happened after the xlog insert as part of a create database and before the actual write out of the PG version file. So if recovery, which always starts from some checkpoint, starts from that checkpoint, then since that wall record predates the checkpoint, it's not even read, and the PG version file will be missing. So the fix in this case was to adopt one of the other documented write-ahead logging coding methods, which is to write the new file before the wall record. That's like we do for create table. And I think a lesson here is it's tricky to write new patterns of write-ahead log coding because they have to interact correctly with concurrent checkpoints, concurrent crashes, concurrent buffer evictions. So keeping sort of all that in your head, or at least my head, is somewhat non-trivial. And I think another lesson here is anytime a patch adds something like an xlog flush function call or a delay checkpoint flag setting, good indicator that it probably deserves some extra review. As far as preventing this systematically, I was thinking that we could run the main test suite, pause after every xlog insert, and then take a backup. And then we could smoke test each one of those backups. In this case, smoke test can catch this pretty easily. You can just connect to every database and one of them will fail. This would take a while, like let's say it would take a day to run. So it would need to be a PG test extra thing, not something we just run every time. Nonetheless, I think it's promising and you could parallelize the smoke test a fair amount. I did not observe either of these corruptions in the field. This was just based on code inspection while writing the previous fix. Here's a fairly different one, more page level corruption within an index. So whenever you delete an empty page of a btree index, this is vacuum doing that. It's a 2-step process. There's a separate wall record per step. The first step unlinks a page from its parent, and the second step unlinks it from its left and right siblings as relevant. So btree scans, they know how to recover if only one of these actions has happened, but amcheck had a check that essentially expected either both or neither of them had happened. So we had a false positive report of corruption if we caught things right between those two write-ahead log records. The relevant link shows dashed red up there, so that's the one that amcheck did not accept having, even though it was actually okay. We could have caught this earlier, I think, with a test that runs point-in-time recovery using the wall from a run of the regular test suite, and then single steps the recovery and runs every amcheck after each wall record. That would be faster than the test from the previous slide. This one could probably finish in an hour instead of a day, but still long enough to belong in PG Test Extra. And in the end, it wasn't actual user visible damage. It was just a false positive. This one's getting kind of far afield, but I'll mention it because I think it's possibly interesting for our future changes. So in PostgreSQL v10, we fixed a bug, Tom actually fixed a bug, in immutable regular expression function results. It involved character classes matching non-ASCII characters. And as an unintended consequence of that fix, queries that use indexes on expressions over those function results could then start to miss rows where the result had changed, because the index didn't update at PG upgrade time, still reflected the old regular expression semantics. I don't plan to do anything about fixing this since v10's out of support for over a year, but I did think about if we were making a change like this again, changing some immutable function, what should we do about it? And a few things came to mind. I think the ideal fix kind of depends on how much of a given index you expect to be changing. So if you're just changing a very small fraction, ideally you want to do something like this where we index all the rows that are going to have to change during the upgrade, and then PG upgrade could change just those rows and things would then be uncorrupt. If on the other hand, almost every row we're changing, then it's more like we would want to build a shadow index that uses the new semantics and then becomes the live index as part of the upgrade process. Either way, you kind of have to ship the future version semantics as an extension to run in the old version, so it's pretty intense. A low effort alternative would be to just mark the index invalid, but that could greatly increase your downtime for PG upgrade, and a lot of indexes weren't affected at all because they didn't use non-ASCII characters. So it's kind of judgment call here. I don't think we necessarily made a bad choice by just not doing anything about it, but I don't know what we would do next time.
Did you run into this one on the field?
Yes. People, upgrading from 9.6 to 11 or 10, and had some of this. In terms of prevention, I was thinking thing we could do would be to log all the immutable function calls that we make during the regression suite, and then sort of replay those on another version and see if any of them have changed. And then we could make an informed decision about whether we like the changes or not. That said, we probably didn't have much test coverage of non-ASCII inputs to regular expression character classes before, or we would have known about this bug before version 10. So I'm not sure that actually would have caught things too well in this case. I can take a pause. Or any questions at this time?
When you get you see a corrupted database sort of instance, do you have a kind of a process by which you track back from there to actually work out what caused that corruption?
Yeah, so I'll actually talk about that more a bit later, but yeah, so far the main thing that has been enough is just to use those pageinspect queries to, and then infer what must have happened based on what they tell me, but I will talk about some harder cases as well.
And you have a bunch of fancy pageinspect queries you're using that you haven't shown. You literally just keep using it directly in the simplest way that's documented. But who can imagine variants? I have a really, really complicated pageinspect queries that I wondered if you.
I don't really have a big library of them. The one I showed is pretty much the main one I use. I'm sure I've done some ad hoc ones, but yeah, I wouldn't be surprised if yours is well ahead of in this respect. All right, this next one I like to call the grant bug. This has been the worst so far. In terms of encountering this one, it arises in a situation when you're running create index on a table that currently, as of that moment, has no indexes. And at the same time, you're running a grant on it. Grant is not necessarily the only way to do it. The thing that's distinctive about grant is that it performs a transactional update on a PG class row without having to hold any lock on the table represented by that PG class row. And if you get that combination, you can then lose the rel has index flag on that PG class row. Now, initially, that kind of has no effects in the sense that rel cache stops loading the index, queries stop using the index, selects stop using the index, updates stop modifying the index. And in that state, you're not actually experiencing any trouble. The problem comes when a future create index statement reinstates that rel has index flag. And now your index comes back from the dead, so to speak, starts serving queries, except that it didn't receive any modifications made while that rel has index equal false state was in place. So you can return wrong query results. This was tougher to diagnose because the index tuples were just missing. There was no record with the right heap tuple ID, but the wrong keys, they just weren't there. And as of when this was reported to me, rel has index was correct. So in fact, I probably only figured it out because there had been a hackers thread the same week I was looking at this, the race condition and PG class thread that talked about a missing rel has index, and that was the clue I needed. So this all arose from a component called the in-place update system that we use to modify rel has index, and we also use it to set things like dat frozen xid, rel frozen xid. That had numerous deficiencies. I ended up finding 5 other bugs. I only thought 4 of them were bad, but then Robert said the 5th one was horrifying, so I guess all 5 of them are bad. But yeah, it turns out vacuum can overwrite the wrong PG class row, so you can have 2 rows for one table and 0 rows for another table.
That sounds bad.
Yeah, I think that officially qualifies in the bad category. Yeah, but you can also, turns out, have other ways of getting to this. Like if you run 2 create indexes concurrently and then one of them rolls back, you can lose rel has index. Also, there's a race condition in the cache invalidation system. I'm guessing this bug has probably affected rel frozen xid more often than it has affected rel has index. But we probably don't notice that as much because if you lose a rel frozen xid update, vacuum just shows up and does it again most of the time. So there's a fair chance we've blamed. Oh, go ahead, Anders.
Have you searched like logs or something for errors from vacuum about like tuples not passing rel frozen xid, where that's not commensurate with like the prior auto vacuums?
I have not done that. That would be a good idea.
I suspect there might be a lot of those. I've seen that in the past.
Yeah, that's a good point. Yeah, there's a fair chance we blame something like this on bad hardware at some point, or PG upgrade, or when it in fact was this bug. So I was mighty tempted to do like a one-line fix, take a stronger lock and grant, but that didn't solve everything anyway. So instead, I wrote the full fix, which is the largest single PostgreSQL bug fix patch series I've ever written. And I've not written the cache invalidation part yet. So the broad design of it is to have commands like grant take a lock tag tuple lock, similarly to what we use for update deconfliction. It does that before it reads the old row content. And then in-place updaters like create index and vacuum, they take the same lock and they wait for any uncommitted grant before they proceed. Now, not ideal to have vacuum block behind grant, but a long-running grant already hurts vacuum just by being a long-running XID, so I think it's probably okay.
Does this affect anyone who uses in-place update?
Yeah. Anyone who uses in-place update on a table that also receives transactional updates, which is all of them, but yeah.
Anyways, I have to talk about this with you.
Sure. Yeah, my patches could definitely use reviews, so if you're interested, race condition on PG class thread could use reviewers. I think a lesson here for me is that the rules that let readers and writers operate concurrently, they're really subtle. There was even a comment in the event trigger code talking about the fact that we lose in-place updates, which was okay for the event trigger code, but I guess nobody had made the connection that not okay for all the other users of in-place updates. It reminds me of how PostgreSQL used snapshot now for decades and would read 2 rows or read 0 rows when it should have read 1. And we got away with it for a while, sort of, but this is kind of a similar level of damage possibility. In terms of systematically discovering such problems in tests, I think it's pretty hard. The RR debugger in its chaos mode could be good for this kind of thing. That said, you would need to think about the fact that grant and create index should be in your transaction mix for this kind of thing. And until you've actually seen it happen, I would not have thought that mix of queries would be important for testing concurrency. In terms of long-term, I think we probably should get rid of in-place updates. Like, we don't actually need rel has index at all. We can just read PG index. Most tables have indexes. That's the harder one, yeah. I'm thinking for those, maybe just thinking out loud, we should have some non-transactional priority queue that gets written to disk for those. That could also avoid the n squared cost that we currently incur to process rel frozen XID updates. If we really don't want to do that, we could move it to a separate table that is only ever in place updated, but then we'd still be O(n) squared, so I'd like to try to avoid that.
Where's the unsquared coming from?
Well, if you have a table with if you have a database with 1 million tables and you vacuum all of them, then each one of them will update its rel frozen XID and then try to update dat frozen XID with a sequential scan of PG class. So you will scan 1 million squared tuples of PG.
Is there a reason we can't use an index to find the PG class row that we want to update?
Well, the initial update, we do that. But then we try to update dat frozen XID, which involves a sequential scan of all of PG class.
Oh, so maybe we need to just not try to update that frozen XID quite so much.
That would be one way to do it. We already help that somewhat because each auto vacuum worker, I think, will do it once, no matter how many tables it updates. But still, you kind of have an amortized n squared over time.
There's actually a new vacuum option to avoid doing the dat frozen XID update. It might be 17, but
16.
yeah, because vacuum DB had exactly this problem, and it was taking forever.
Yeah, so that is available if you kind of hand modify. If you don't rely too much on auto vacuum and you drive the auto vacuuming yourself, you can use that feature. So we'll see what happens with that. To your question, I thought I was going to run into some very difficult cases where I would not be clear how we got to the corrupted state. So the way I was thinking I would approach that would be take the wall archive and then bisect within that range to figure out which wall record the corruption started at. So for example, the grant bug, it would find the first in-place update record of the second create index statement. pglogical bug, it would find just the commit of the modification that should have created an index entry and did not. This is kind of like git bisect is what I had in mind. I didn't end up having to do this. I think I got this plan from somebody else probably in this room, but I don't remember which of you gave the idea, so thank you for the idea. This did lead me to some feature wish list items for things that could make diagnosing this kind of thing easier. So I'll just share them kind of quickly. Be great to have amcheck for more access methods. It would be great if heap all index for a table with multiple indexes had some way not to scan the table for every index. So like maybe we make the index build table scan able to generate multiple indexes worth of columns at once. That could help. Pretty small tactical thing, like if the Bloom filter reaches 100% for heap all index, we should probably just stop there and say, oops, you want to raise maintenance work mem because we can't actually report any error here. So none of these are crucial gaps. I'd welcome anyone working on these. I'm definitely, what I'm doing is the opposite of claiming them. Opposite of cookie licking. Beyond amcheck, one thing I've noticed here, it's kind of a broader topic, but we have a bunch of error messages that are expected to never happen. Things like unknown type of JSON B container or compressed PDLZ data is corrupt. And these are okay if you have a reproducible test case and you have a debugger attached. But if you don't have both of those things, it's really hard to do anything with a message like that. So like the PGLZ one, it could be a bit flipped in a compressed datum, or it could be the datum was never compressed and just somehow reached the compressor, even though it wasn't. So perhaps these sites could, I don't know, they could hex dump a few bytes around the area, or maybe they could save some bytes to a file in the data directory. I don't know, but something so that there's actual information about the bytes that confuse the site in question. And I think Robert Haas expressed a similar sentiment on the list not too long ago. About
one thing I've noticed is that when we have bad compressed toast data, the detoaster likes to crash the entire server as a response to there being some wrong bytes on disk, which I have found that users don't always appreciate that particular way of handling that situation.
It is discouraging, yes. Yeah, that's, I think I can skip over these other ones. That's the main bulk of what I wanted to discuss. So thank you all for joining. I'm happy to take questions.
Great talk.
Thanks.
I found it very interesting to look at IO error, and that preceded a lot of corruption in Postgres data directories. And sometimes I think it was the disk dying, but also sometimes I think we reacted right. Like I found some instances of like old bugs where we didn't handle checkpoint errors correctly, stuff like that. But I think we might have some others that I haven't been able to track down.
So this is like when we're trying to write out a buffer and it gets EIO, that kind of thing?
Like sometimes it's over 10,000 bytes or something, but like this is all versions, so I wasn't able to like unify it, but like we're a lot of different places because we do IO in lots of places, and then to get random errors, like I don't know, reading the control file, doing like backend startup or something, I don't know.
Yeah.
So we consequences.
Question for so as I'm sure you know, users are now able to use amcheck, which has a friendlier interface. It's more accessible, high level. Using amcheck directly using an SQL interface that's unfriendly, sure, doesn't describe the problems in practical terms that are relatable to users. amcheck is doing better there, but maybe there's room for improvement. Overall, my sense is that there's not a great understanding of what you ought to be doing given your requirements, So do you have any thoughts on questions that users ask me that I have no idea how to answer, like how often should I be doing this? What settings should I be doing? Is there some kind of theory about how to think about these things that you've come up with in practice? What works? That sort of.
Well, I think it's useful to run pgamcheck in a time frame tied to your wall retention, so that you have wall covering both the uncorrupt and the corrupt moment. So that's one thought I would have.
Theoretically, it's useless because it's checking something that should always be true, right? So there's no like that is all the way true. So there's no like good cadence to run it out. It's basically what you can tolerate, what seems, if you have a period of inactivity, maybe do it then, that sort of thing. It just seems, if it was presented better, if the high-level interface presented by pgamcheck could be improved, users would use it more often. It could be a virtuous circle perhaps from that. But I don't know how to get that going.
Yeah, and I also think of it as correlated to any large changes in your storage subsystem. I think you've talked about how it's great for detecting non-crash safe storage. So you buy a new server, you upgrade to a new kernel, major version. Those could be great times to increase the frequency of your amchecks.
Obviously, your examples were just due to bugs in the code, but in terms of some disk corruption, is there, I don't know the internals obviously of Postgres, but are there features within Postgres that do block checking before they're written? And so, like checksums or anything like that?
There are block level checksums. They're done when you read the page back in. So that's more likely to detect things like single bit flip, as opposed to, it would be difficult to construct a single bit flip that passes page checksums but fails the logical checks in amcheck. Jacob?
Kind of a follow-up to Peter's. PG Upgrade has the concept of its pre-flight check that you can run against the web database. I'm wondering, would it be advantageous maybe to run some of the AM stuff? I don't know if you could sample some data from the live and maybe do a pre-flight check against, the index pieces, if that's an issue that causes anxiety during, user upgrades. I don't know if that would be worth the complexity or not, but.
Are you thinking like in the context of that regexp bug that happened to PG Upgrade? Yeah, it's tough to find the balance between making the upgrade take longer for people who don't have anything to detect and people, I guess looking back, another low effort way we could have dealt with that would be to just report you have some index over regex and that could be affected. So now you know.
I think it's actually a good point not to mix it up together, because like upgrade is very special procedure and then it would be more complex. It's complex enough already. So maybe it's a good idea to run unchecks, for example, while you're planning an upgrade. So
Yeah, I think
minimize the chances.
I think it's better for the user to decide that, right? Like we could suggest it as a thing that might make sense, but I'd be reluctant to put it in the tool.
Any other questions? Andre?
How do you think, would it be good idea to move checksums from pages to maybe some other fork relation? So that now if we have some corruption that is actually introduced by hardware, if we have bug in page cache or something similar, we read in stale version of page, then it's not corresponding to index, but we are not sure. If we could read checksum from another place, we would know that it's not coherent.
Less correlated, is that what you have in mind?
Yeah.
Makes sense.
It would be much harder to do because it's easy when you have this 8 kilobytes and you check it that it's incoherence. But the corruption is itself incoherence of two systems.
I think it would be difficult because, if the separate checksum fork disagrees with the page, is that because the page is corrupt, or because the crash itself wrote one of those things to disk after a modification, and the other one didn't make it to disk after the corresponding modification?
Let's keep it with the LSN.
You need double page writes.
Yeah. And log that checksum.
Yeah, we'd have to think about the I/O amplification for sure.
I've got another question actually I just thought of. Is amcheck ever crashy for you if you have corrupt data? And if so, do you think we should do something about that? It could be more robust, especially the btree checker in some aspects. It's not, I did improve it a few years ago, but
I have not personally encountered amcheck crash, so looks good from my perspective.
I know Mark Dildred did some testing and he found it quite easy to crash, but he was also trying to crash it.
Right, so I'm sympathetic to that, to a point, of course. I mean, I can always find a way. It's user-defined code. I can just invent a case always that is going to make it crash. So we know that that's not the guarantee we're making. But if I had any practical experience pointing in the direction of it could be less crashy, I wouldn't mind doing that. It wouldn't be terrible. You could do things like, well, what we're doing now. You could, for example, you want to validate line pointers against index tuples that we currently do. Some of that, there could be more. We could also be more paranoid about when we're looking at tuple offsets, we could be more careful there. But it doesn't seem to be a huge problem. I mean, I might work on that if there was any evidence of.
I guess I should correct my statement. He wasn't trying to crash it, but he was using random.
Okay, that is worse. So, yeah.
Yeah, and I should say that I think 100% of the instances that I used here had page checksums enabled, so anything that violated that would not even reach amcheck, so that probably helped me not get crashed.
That hard anyway, so maybe I should just do it on the off chance.
Yeah, and maybe just to end on a happy note of some kind, that I think there are really only three kinds of bugs in Postgres. There are ones that are very rarely encountered. There are ones that are very low impact, and there are ones that are very new. So most of these are in the rarely encountered, maybe high impact, probably not new category. So Postgres has great data integrity. This is just the fringes of it. Thank you all for joining.